All right. So we're working with solving trig equations using identities part 2. Yesterday we worked primarily with Pythagorean identities, reciprocal identities, and a few quotients, depending on how you view the cotangent and the tangent. Today we're going to work specifically with double angle identities. All right. So we have 3 different examples to kind of show you how they're going to work. So let's get started. So we know that cosine of x, 5 cosine of x plus a 3 cosine of 2x should equal a 3. So we're off to a good start because I see a cosine of x in both of them. However, the issue is that the inputs are not the same. So that does not work for us here. So since I have a cosine of x, like 5 cosine of x, I see the cosine of x. That's my hint that I need to use a double angle identity for cosine of 2x that would give me a cosine of x of some form so I can actually work with that. So I know that cosine of x is equal to 2 cosine, to 2 cosine squared of x minus 1. So I'm going to do that substitution. So I'm going to have 5 cosine of x plus 3 times 2 cosine squared of x minus 1 should equal 3. So now that works for me because now I have cosine of x, and now I see this more as a quadratic, so I can do some factoring to solve. So simplifying this, moving the 3 to the other side, I will eventually end up with 6 cosine squared of x plus 5 cosine of x. 3 times 3 times a negative 1 is a negative 3 minus 3 gets me a negative 6 is equal to 0. Right? And so the reason I do that is because now I can go ahead and do some factoring. And whether you use however you factor, you should end up with something like this. 2 cosine of x in one parentheses, 3 cosine of x in the other parentheses. It has to be 9 and 4 to get a positive 5, so plus 3 minus 2 equals 0. Okay, so that's just the way I factored it real quick. If not, you can pause the video, do it your way. Make sure you end up and understand where I came up with the 2 cosine of x plus 3 and a 3 cosine of x minus 2. So then I go ahead and do that. And now I can set my factors equal to 0. So 2 cosine of x plus 3 equals 0, meaning that cosine of x should equal a negative 3 halves, which means no solution because cosine produces values between negative 1 and positive 1, including negative 1 and positive 1. So anything outside that range, not possible, so no solution. For the other one, when I look at 3 cosine of x minus 2 equals 0, I can see that cosine of x should equal 2/3. And this is where I have to do some work because cosine of x can equal 2/3 because it falls within the range of negative 1 to positive 1. However, 2/3 is not one of the values from my unit circle. So this is where I'm going to go ahead and use my arc cosine, the inverse cosine function. So arc cosine of 2/3 should equal x, which means that x should equal about 0.8411, right? And that's going to be in the first quadrant because cosine is equal to a positive number in the first quadrant and the fourth quadrant. So using my rules for the arc cosine, I can get my second possible principal angle if I just use the negative version of this answer. So because I don't have an interval that I'm trying to find answers within still, I just leave that and I generalize my answer, plus 2n pi. Or I could say that x should equal about negative 0.8411 plus 2n pi. And so that's it for that first problem. All right. If I go to the second problem, I have sine of x multiplying a cosine of x should equal 1. So sine of x times cosine x, that looks very familiar. That looks like sine of 2x. So in my mind, when I see that and I look at my doubling identities, I know that this is very similar to the sine of 2x. Except sine of 2x should equal 2 sine of x cosine of x. So the fact that I just have 1 sine of x cosine of x instead of 2 sine cosine of x means that I can think of this as 1/2 sine of 2x should equal 1. Because that's what I currently have. So, since I know 1/2 sine of 2x should equal 1, then I can just go ahead and try to solve for sine of x. So that means that sine of 2x should equal 2. Because to get rid of that 1/2, you just have to double both sides. So then you have sine of x is equal to 1. I'm sorry, sine of 2x is equal to 2. And we could try to do a u substitution right now and think of it as sine of u should equal to, right? If u is equal to 2x. That means I'm looking for solutions where sine of u would equal 2, and then I would take those and go ahead and try and solve for x, like we were doing at the beginning of the month, like end of April. However, like I previously stated, sine and cosine have very similar ranges. They both go from -1 to +1 unless they're transformed, in which case this has no solution because sine will never equal a 2 like this. That's the way it rolls. But that's okay. We'll get them next time. We could also look at the third one where we see cosine squared minus sine squared is equal to 1/2. Now that one should be very easy to look at because I know cosine squared minus a sine squared, that is what cosine of 2x equals. So I can just go ahead and replace this with cosine of 2x equals 1/2. And then I can do the u substitution again, like if u equals 2x, then I'm really trying to figure out where cosine of u will equal 1/2. So that means u would have to be pi over 3 plus 2n pi, or u would have to be, let's see, it's got to be in the fourth quadrant, so 5 pi over 3 plus 2n pi. And so from there, since I know what u should equal, well, that means that 2x should equal pi over 3 plus 2n pi. And 2x should equal 5 pi over 3 plus 2n pi. So in order to figure out what x should equal, I'm going to have to divide both sides by 2. So that means x should equal pi over 6 plus n pi, and and x should equal 5 pi over 6 plus n pi. All right. So that's how the double angle identities go. The basic idea is when you're trying to work through these problems, if you see something that resembles a double angle identity, go ahead and do the replacement. Substitute that expression that you see with a double angle identity, solve for that given angle, and then if, using the u substitution like I did, then once you know what that u equals, replace it back with the given, like with the 2x, and solve for x from there. I will say this kind of as an important note. If I was looking like this last problem, if I was looking for answers between 0 and 2 pi, then you have to be careful and really think about what you did. This is one solution. This is another solution. Both of these angles fall between 0 and 2 pi. So when I'm asked to find solutions within a certain interval, I'm not looking at the principal angles that I found. I'm looking at the angles I got at the very end and seeing, well, okay, do they fall within this range of 0 to 2 pi? They would. However, consider this. So that means that pi over 6 is a solution. If I find a coterminal angle for pi over 6, I would get 7 pi over 6. 7 pi over 6 falls within the interval of 0 to 2 pi. If I try to find another coterminal angle from the pi over 6, I would end up with 13 pi over 6. That does not fall within the interval that I was asked to use, so that wouldn't count. Same with the 5 pi over 6. 5 pi over 6 would be one possible solution if n is equal to 0. If n is equal to 1, then I could get 11 pi over 6. That falls within the interval of 0 to 2 pi because I can think about 2 pi as 12 pi over 6. So notice, even though you found your two principal angles, if this problem was asking you to find solutions within a certain interval, once you have your generic answer, find coterminal angles and make sure that those coterminal angles you find fall within a given interval. And that's all you really have to do with these. So keep that in mind because you will have a problem, maybe two, that will ask you to work with that tomorrow.